This is Unit 15, Equilibrium, pages 153 to 160. Now we'll get into the part of equilibrium that is performing calculations using what's called ICE tables. So we have example 15.53. You have a mixture of 0.25 molar nitrogen, 0.35 molar hydrogen, and 0.003 molar ammonia that exist in a closed container. The reaction proceeds towards equilibrium, so that tells you that right now it's not at equilibrium. When the equilibrium mixture is analyzed, 0.313 molar hydrogen is found, so that is an amount we know of hydrogen when it is at equilibrium. Calculate the equilibrium constant. So first, I have taken the equation that we're given and I've rewritten it here, and I've written ICE, which stands for initial concentrations, the change in concentrations, and the equilibrium concentrations. So K for this equation, the equilibrium expression would be ammonia squared divided by nitrogen times hydrogen cubed, the concentrations of each. And so the question is, what is K? And so in order to find K, I'm going to have to take whatever the value of ammonia is at equilibrium and square it. And then I'm going to have to divide the value of nitrogen times the value of hydrogen cubed. We actually do know the value of hydrogen. They tell us when the equilibrium mixture is analyzed, 0.313 molar hydrogen is found. So I do know that this value right here is 0.313. But what are the other two? So first, I'm going to take the initial concentrations, which were given. This is 0.25. This is 0.35, and this is 0.003. The change in concentrations is based on the stoichiometry. And because these are the reactants, I'm going to assume they are disappearing and the products are appearing. And so we'll say minus x minus 3x and plus 2x. So it's negative because I'm assuming that this is these reactants are becoming less and my products are becoming more, and so that's why that's labeled as a positive. So negative 1x because the coefficient is 1, negative 3x because the coefficient is 3, and plus 2x because the coefficient is 2, and this is the products are appearing. Now, you always want to take your I plus C, and that is equal to E. I plus C is equal to E. So 0.25 plus C, or minus X, so combined I and C, and that's going to make my E. Hydrogen is going to be 0.35 minus 3x, and ammonia is 0.003 plus 2x. Now these are the concentrations at equilibrium. We have already been told that this 0.35 minus 3x is equal to 0.313 for hydrogen, because that is the concentration at equilibrium of hydrogen. So because I know this piece of information, I can actually figure out what is the value of x. So I'll take 0.35 minus 3x equals 0.313, subtract 0.35 from both sides, and I'll have negative 3x is equal to negative 0.037, and then divide both sides by negative 3, which gives me x equals 0.0123. So now that I know the value of x, I can plug it in to here and here to determine what is nitrogen's concentration at equilibrium. So if I do 0.25 minus x being 0.0123, I get a concentration for nitrogen equal to 0.2377. So that is this concentration at equilibrium for nitrogen. And then I can plug in here for hydrogen 0.003 plus 2 times 0.0123, and this will get me the hydrogen concentration. And when I do this math, I get the ammonia concentration. And when I do this math, I get 0.0276. And so that is the value that I place up here. Now I can do this math in order to find K, and when you multiply this squared divided by this cubed, you get a K is equal to 0.105, and that is the equilibrium constant. Example 15.54, a closed container is loaded with an initial BRCL partial pressure of 1 atmosphere. So I have 1 atmosphere of this to start. Calculate the partial pressure of this at equilibrium. Assume that initially bromine and chlorine are 0. So I've rewritten the equation like this, and I've also gone ahead and jotted down the Kp. We're dealing in pressures, and the equilibrium expression, which is going to be Kp equals BRCL, the partial pressure, BRCL squared, over the partial pressure of bromine and the partial pressure of chlorine. So now we'll set up our ice table. And the initial concentration of these are each 0 atmospheres, and this is 1 atmosphere. The change is going to be, so see how these are 0? That means I must be forming these, and this must be disappearing. So I'm going to call this positive 1x, or just x. This is going to be positive 1x, or just x. And this is going to be negative 2x. So remember that at equilibrium, it's I combined with C equals E. So if I combine 0 and plus x, I get just x. 0 and plus x is just x. 1 and negative 2x is 1 minus 2x. So I don't know any of these values, and I don't have any equilibrium concentrations in order to figure out x. But what I do know is what the value of K is here. And so what I'm going to do is set up the equation where I'm going to substitute in the value for K here, 7.0 equals, and then in place of BRCL, I'm going to go ahead and put what BRCL is at equilibrium, which is 1 minus 2x, and then that's going to be squared. So you're going to put 1 minus 2x, and this will be squared, and this is over, and then this is x, and this is x, and so x times x gives me x squared in the denominator. So this actually gives us a situation where we have squared over squared, and in that case, we can actually take the square root of both sides of this equation. And the goal here is to solve for x. So the square root of 7 is 2.646 equals, and then the square root of this just cancels with that squared, and so that leaves me with 1 minus 2x over x. And so now I can solve for x. I'll multiply both sides of the equation times x, and that's going to give me 2.646x equals, this cancels, 1 minus 2x. I'll add 2x to both sides of the equation, which will give me 4.646x equals 1, and then I'll divide both sides by 4.646. And so this will cancel, and I get x is equal to 0.215. Now, make sure you understand that all we have solved for is what the value of x is in here. However, what I want to know is what is this concentration at equilibrium. And so I'm going to have to actually substitute in my x into this equation to find that. So I'll have 1 minus 2 times 0.215, and that's going to give me the partial pressure of BRCL at equilibrium. And so when I do this math, I get 0.570 atmospheres. And then obviously, since this is what x is, that means at equilibrium, my partial pressure of bromine is 0.215, and my partial pressure of chlorine is also 0.215. Example 15.55, a closed furnace is loaded with excess nickel oxide and nickel solid. Two gases are added at the partial pressures of 200 torr and 150 torr. The furnace is heated to 1600 Kelvin, where the equilibrium constant is Kp equals 600. What is the equilibrium partial pressure of the carbon dioxide? So first I've rewritten the equation here, and it's important to note that we do not include solids in our equilibrium expression because they just equal 1. So I'm actually going to rewrite this without the solids just because it's friendlier to my eyes when I'm doing this calculation. So I'm going to write the equilibrium expression, which is Kp equals the partial pressure of CO2 over the partial pressure of CO. We are told that we have a Kp of 600. The ICE table will be written as follows. The initial concentration of the carbon monoxide is 200 torr and the initial of carbon dioxide is 150. The changes, I'm going to assume that this is minus 1x and this is plus x. It really wouldn't matter which one you make negative and which one positive as long as they're opposite signs. However, you can figure out by calculating your Q which direction the reaction is going to predominantly move in order to know whether or not to put the negative here or the positive here. 150 divided by the 200, I get a Q of 0.75, which is much smaller than the K, and therefore the Q is moving towards the right to get to K, which means that the reaction is predominantly moving the product. So this is disappearing, this is appearing. Remember that the equilibrium is the I combined with C, so this is 200 minus X, and this is 150 plus X. And the goal is to figure out what is this value right here, but I need to know what X is first. So I'm going to go ahead and plug in these two values in my equilibrium expression, knowing that the K is equal to 600. So I'll have 600 is equal to CO2, which is 150 plus X, over CO, which is 200 minus X. I will now multiply both sides by 200 minus X. And that's going to give me, I'm going to distribute the 600 here. That's going to give me 120,000 minus 600X is equal to 150 plus X. I'm going to go ahead and subtract 150 from both sides, and I'm going to go ahead and add 600X to both sides. This is going to give me, remember that this is minus 150, 119,850 is equal to 601X. Divide both sides by 601, and we get an X equal to 199.4. Remember, this is just what the value of X is. However, what I need to know is what is this value here. So I'm going to plug my X into this equation. So I'll do that here. The partial pressure of CO2 at equilibrium is going to be equal to 150 plus 199.4, which is equal to 349.4 atmospheres. So here's a little note card for you as reference. An ICE table is going to be written where you write the equation. I stands for initial concentration for each of your reactants and products. C is the change in concentration, and that's going to be based on the stoichiometry. And it's either going to be minus or plus depending on which direction the reaction is going, what's disappearing and what's appearing. And then you include the stoichiometric coefficient here as well. The equilibrium concentrations are going to be the combination of I and C to get your E. And remember, the equilibrium concentrations are what can be placed in the equilibrium expression for the reaction. Special circumstances, you might have to use the quadratic formula. If that's the case, never choose the negative of the two answers that you get. Nor do you want to choose an answer that'll end up being negative once you plug it in and solve for X. Perfect squares, take the square root of both sides of the equation. You might do what's called the estimation based on 5% rule. We'll go over that more in a later video. And all equilibrium concentrations must be positive values.